The James Webb Space Telescope has detected a deviation, a small, silent twist in the darkness that shouldn't exist. An interstellar object, roughly the size of Manhattan, has begun to drift off its predicted path. Its name is 3I/ATLAS, and for weeks, scientists believed it would pass harmlessly through the outskirts of our solar system. Then, in a sequence of infrared frames no one expected, it changed course. Inside control rooms across the world, data streams flickered red. JWST spectrometers showed a flicker of gas bursting from its surface, followed by an imperceptible yet undeniable shift in velocity. Orbit tracking software recalculated trajectories, and every new line on the chart inched closer, not outward, but inward. For the first time since humanity began mapping the heavens, an object born under another sun appears to be steering itself toward ours. Professors, engineers, and amateur astronomers alike froze at their monitors, whispering the same word: impossible. This isn't a routine comet. It's a traveler from another star system, older than our own sun, glowing faintly blue in the void. And now it's coming closer. Every instrument we own is watching. The air around the news feels electric, like the moment before a storm. No one knows what's causing the deflection. A natural jet of carbon dioxide, radiation pressure, or something far stranger. What we do know is that we're witnessing motion across the boundaries of the galaxy itself. For the next few minutes, we're going to trace this story: how the James Webb Telescope uncovered the anomaly, what scientists think is happening, and why some of them believe this might be the most important cosmic event of our generation. Because the universe just blinked, and it blinked back at us. Professor Loeb had been warning for years that interstellar objects might not behave like anything we know. When 3I/ATLAS first appeared in the ATLAS survey data from Hawaii in July 2025, he immediately recognized the pattern: high inbound velocity, hyperbolic orbit, and a chemical spectrum too cold for local origin. The first two interstellar visitors, Oumuamua in 2017 and Borisov in 2019, had been brief flashes racing past the sun and vanishing into the dark. This one, however, was slower, heavier, and strangely reactive. At discovery, it was traveling more than 130,000 miles per hour on a retrograde path, moving opposite the planet's direction. That alone made it a celestial outlier. Observatories from Chile to the Canary Islands confirmed its brightness curve, and within days, NASA and the ESA retasked the James Webb Space Telescope to observe it. For the astronomical community, this was Christmas in July, a chance to watch an object from another star pass through the heart of our system. Yet from the first week, something felt off. Its coma, the halo of gas and dust, expanded faster than any model predicted. The color ratios didn't match water-based comets. Instead, they screamed carbon dioxide, methane, and other frozen volatiles that shouldn't survive near our sun. Loeb speculated on podcasts and conferences that maybe, just maybe, this was no ordinary rock. Perhaps it was a probe, a fragment of something designed, adjusting its path as it entered warmer space. Most scientists dismissed that as fanciful, but none could ignore the data. The numbers weren't stable. Every update from the Minor Planet Center came with a smaller confidence interval and a larger mystery. What exactly was pushing 3I/ATLAS off course? Was it physics as we knew it, or physics we had yet to understand? The James Webb Space Telescope was built to peer across billions of years, not to chase comets. Yet in late August, mission planners pivoted its golden mirrors toward a dim, fast-moving blur cutting across the black. Using its mid-infrared instrument, JWST captured a glow unlike any in its vast archive. An emission spectrum dominated not by the familiar signature of water vapor, but by carbon dioxide. That single ratio changed everything. Ordinary comets form within warmer zones near their stars. They carry abundant water ice and lose it first when heated. But this visitor was different. Its chemistry suggested birth in the frozen outskirts of a dying star system, perhaps around a dim red dwarf where the sunlight was so faint that even nitrogen turned solid. There, for billions of silent years, it drifted beneath cosmic frost. Its surface hardened by radiation until some distant gravitational encounter hurled it across interstellar space and, by unimaginable chance, into our path. When JWST began its spectral analysis, the results unsettled even veteran astronomers. The comet's emissions pulsed in a slow rhythm, as if exhaling ancient gases that had been trapped since before Earth's formation. Each release came in precise intervals, bursts of vapor venting from fractures that glittered with reflected sunlight. To the instruments, they resembled heartbeats in the dark. Each pulse acted like a microscopic thruster, altering its momentum by a fraction of a meter per second, infinitesimal in isolation, yet monumental over cosmic distances. Ground-based teams noticed the same periodicity in optical data. The plumes' symmetry was uncanny, their angles almost mathematically clean. "It's as if the jets fire in rhythm," one analyst murmured. Others dismissed it as coincidence. But when multiple observatories confirmed identical timing, coincidence began to feel less comforting. By September, JWST had mapped the composition of the plumes: CO2, carbon monoxide, and trace hydrocarbons, volatile relics of an alien nursery. Embedded within them were hints of heavier elements like nickel and magnesium, suggesting a complex interior layered with dust and frozen metal grains. To physicists, this was not just a comet, but a living record of a different star's chemistry. For JWST, it became the most intimate study of alien material ever undertaken. For humanity, it was a quiet awakening, proof that the universe isn't a static backdrop of stars, but a moving system where even the ancient and the distant can reach out, veer toward our sun, and remind us that motion, not stillness, is the rule of creation. At first, the orbital plots looked perfectly safe, a smooth arc looping past the sun before escaping toward the constellation Lyra. Nothing to worry about until September 10th. That morning, a new dataset arrived from the Pan-STARRS Observatory showing subtle deviations. When NASA's Jet Propulsion Laboratory ran the updated model, the curve no longer widened, it tightened. The red prediction line bent inward, crossing closer to the orbits of Venus and Earth. In the JPL Control Center, silence replaced routine chatter. Every 30 seconds, the simulation refreshed, and every time, the object's predicted course shifted a little more toward the inner solar system. Engineers double-checked software, assuming an error, but the second run matched the first. 3I/ATLAS was changing its path. Initial theories pointed to natural forces, uneven outgassing, solar heating, or the gentle shove of radiation pressure. Yet none of those explained the precision of the shift. The deflection occurred in consistent increments, like an invisible hand applying steady torque. One astrophysicist compared it to a spacecraft correcting its trajectory using controlled bursts. Soon, Loeb reignited a familiar debate, one that began years earlier with Oumuamua. Could an interstellar object steer itself, either by natural feedback loops or engineered intent? Critics countered that frozen CO2 could easily mimic propulsion through reactive jets. But as James Webb Space Telescope and Gaia confirmed repeating emission cycles, the question became unavoidable. This wasn't random drift, it was motion with pattern. Across the world, models multiplied. Simulations showed that if the current acceleration continued, 3I/ATLAS would pass near Earth's orbital path on December 19th, 6 days before Christmas. Not a collision course, but a proximity so close that its coma could reflect enough sunlight to be visible to the naked eye. The news rippled through observatories and online communities alike. Suddenly, every major telescope from Chile to Japan prepared for coordinated observation. Spacecraft operators checked whether existing probes, Mars orbiters, the Parker Solar Probe, even the aging SOHO satellite, might capture incidental readings. By early October, one phrase circulated quietly in research channels: space isn't supposed to change its mind. Yet here it was, a cosmic vagabond rewriting its own route under our watch. Whether guided by nature or something beyond, 3I/ATLAS had become more than a comet. It was a moving question mark hanging between stars and science. When the deviation reached the public, the scientific world erupted into coordinated chaos. The European Southern Observatory organized nightly monitoring sessions, synchronizing with NASA, the Indian Space Research Organization, and Japan's Subaru Telescope in Hawaii. For the first time, data from multiple hemispheres streamed into a shared real-time server. Humanity's instruments, spaceborne and terrestrial, turned as one toward a single point of light. Inside virtual conferences, the atmosphere teetered between exhilaration and fatigue. Every time a new image arrived, someone's model broke. The object's velocity oscillated, its coma shimmered, its luminosity fluctuated without pattern. "It's like chasing a heartbeat across light years," one researcher muttered. Meanwhile, social media turned the mystery into a global obsession. Hashtags like #Atlas approaches and #Interstellar visitor trended for days. News outlets recycled footage of scientists looking skyward while headlines screamed, "Alien probe adjusts course toward Earth." NASA's press office spent entire nights drafting clarifications. No impact threat, no confirmed anomaly, but continuing observation. Behind the scenes, however, unease grew. NASA's Planetary Defense Coordination Office began quietly recalculating orbital probabilities. The results remained safe, yet uncertainty increased instead of decreasing, a statistical paradox. "We're not predicting a collision," one engineer told Nature, "but we're also not predicting stability." JWST, meanwhile, delivered images that deepened the mystery. Its infrared cameras caught a faint plume extending from one hemisphere. Not chaotic, but shaped like a spiral. Dust particles seemed to curve outward in disciplined arcs, implying rotational control. Hubble confirmed the same structure in visible light. To some, it looked eerily engineered. As October drew to a close, international teams proposed an emergency observation campaign during the object's December approach. The European Space Agency repurposed Gaia's astrometric sensors to capture its micromotions with unprecedented precision. The goal, to determine once and for all whether 3I/ATLAS was merely venting gas or subtly thrusting under self-directed influence. The realization settled over the astronomical community like static. They were no longer watching a visitor pass by. They were witnessing a transformation unfold in real time. The object's coma thickened, its jets strengthened, and its trajectory bent a fraction closer to the sun each day. "It's like it knows we're observing," whispered one analyst during a midnight feed. The line was half a joke, half an admission of awe. No one laughed, not because they believed it, but because no one could prove it wrong. Let's be clear, 3I/ATLAS poses no direct threat of collision. Even at its closest predicted pass, the object will remain well beyond lunar distance, a harmless wanderer framed against the cold. Yet its unpredictable behavior exposes the limits of our surveillance. Our planetary defense network was built for near-Earth asteroids, slow, local bodies moving in well-charted ellipses. Interstellar visitors rewrite those rules. They arrive unannounced, streaking in at tens of kilometers per second from random inclinations. The early warning window shrinks from years to weeks. Atlas proves that even a small outgassing jet or radiation push can bend an inbound trajectory by millions of kilometers before we notice. At NASA's Planetary Defense Coordination Office, analysts have started folding non-gravitational variables into hazard software. They're modeling sublimation thrust, anisotropic mass loss, even the minute sail-like effect of reflective dust. "This is our stress test," one engineer said. "If we can predict ATLAS, we can predict anything." The object's evolving coma also opens rare opportunities. Lunar telescopes and Mars orbiters will analyze its tail composition as it passes, tracing interstellar isotopes never sampled before. If fragments break off, some might drift into Earth's orbital plane months later, burning up as micrometeors that briefly streak alien chemistry across our atmosphere. Instruments like NASA's ASIM on the ISS are preparing to capture those signatures. But beyond the science lies symbolism. Humanity built the most powerful observatory ever launched, and now that telescope is watching something foreign approach the sun. For all our technology, the message is humility. The universe doesn't schedule its surprises. Cosmic proximity isn't a disaster movie scenario. It's an invitation to observe, to learn, to remember that we are participants, not spectators, in a living solar system. No matter how many press briefings urge caution, the speculation will not die. Each new shift in 3I/ATLAS's course reignites headlines. Is it steering itself? Artificial probe theory revived. The echo of Oumuamua hangs over every discussion. Avi Loeb's argument remains simple. When an object from interstellar space exhibits continuous directed acceleration without visible exhaust, the possibility of design, however remote, must be considered. With ATLAS, the case is subtler. Its CO2-driven jets could, in principle, account for the motion. Yet JWST's high-resolution spectra show the plumes firing in near-regular intervals, almost rhythmic. Its spin has stabilized instead of tumbling chaotically. And now nickel vapor, metallic, reflective, thermally resilient, has been detected within its coma. To engineers, nickel is the skeleton of spacecraft. To astronomers, it's a puzzle. Those who resist the alien craft hypothesis warn against anthropomorphizing nature. Comets, they remind us, are full of surprises. Sublimation can pulse when subsurface pockets open, and symmetry may simply be chance. Still, the line between coincidence and curiosity keeps thinning. In quiet moments, even skeptics admit this object behaves intelligently. Meanwhile, simulation teams experiment with theoretical self-steering comet models, asking whether natural jets alone could maintain such precision. Early results suggest that a body of Atlas's mass would require exquisitely balanced outgassing, a feat rare in nature but not impossible. So the debate becomes philosophical. When observation exceeds explanation, do we assume life or deeper physics? Perhaps both. Whether it's a relic of alien engineering or an exquisitely tuned natural mechanism, 3I/ATLAS forces us to expand the boundaries of plausibility. For the public, it reawakens a cosmic imagination dulled by routine space news. For scientists, it's a mirror demanding intellectual humility. We may not yet know what it is, but we can no longer pretend the galaxy is silent. Set aside the controversy, and the hard data alone is staggering. The isotopic ratios emerging from JWST's and ALMA's spectrographs suggest a chemistry foreign to anything cataloged in our solar system. The carbon-to-oxygen balance skews heavily toward carbon. The nitrogen isotopes resemble readings from the outermost protoplanetary disks observed around distant dwarf stars. That composition tells a story of extreme cold. 3I/ATLAS likely formed in a region so far from its parent sun that even nitrogen froze solid. When its star aged or collided with another body, gravitational chaos flung it free. For perhaps billions of years, it has wandered, gathering cosmic radiation that etched a dark crust over its ices. Now, under our sun's heat, those layers are venting, exposing the pristine material beneath. The molecular memory of another world. Astrobiologists see a larger implication. Such wanderers may be the galaxy's messengers, ferrying complex organics from system to system. Meteorites on Earth already show amino acids older than the planet itself. If interstellar debris routinely drifts through young planetary disks, then panspermia, the seeding of life's ingredients across the stars, moves from myth to mechanism. For planetary scientists, ATLAS is also a dynamics laboratory. Watching how its mass loss alters spin, orbit, and structure reveals how comets evolve near stars. Those insights refine models of solar system formation, showing how early comets may have delivered volatiles to Earth. Even its nickel traces hint at processes that bridge chemistry and metallurgy, possibly clues to how metallic cores in planets begin. To study 3I/ATLAS is therefore to glimpse not only an alien origin but our own ancestry. Every plume of vapor it exhales is a whisper from another epoch, reminding us that nothing in the cosmos truly stands alone. Star systems exchange dust the way oceans exchange currents. Creation is communal. Across the world, humanity watches together. Live streams count millions of viewers. Children stay up late to glimpse a speck that may have traveled for eons. In city parks and mountain observatories, telescopes turn like flowers following the same celestial guest. For a brief moment, the divisions of language and politics dissolve under the shared glow of curiosity. It feels almost ceremonial. Ancient civilizations once gathered to interpret comets as omens, harbingers of war or change. Now we gather to interpret data, yet the emotion is identical, awe wrapped in uncertainty. Philosophers see in ATLAS a parable of migration and resilience. Here is a body exiled from its home, scarred by radiation, carrying the chemical DNA of its birthplace, yet still luminous under a foreign sun. In its endurance, we recognize ourselves, wanderers, displaced yet determined to understand. Scientists too are changed. The object humbles them, reminding the most analytical minds that knowledge is provisional. Each night the models update, and each morning the universe proves larger. We used to think of the solar system as a fortress, one astronomer says. Now it feels like a harbor with open seas. In classrooms, teachers use the live feeds to explain gravity, thermodynamics, and cosmic history. Children sketch comets with tales of alien fire, and somewhere in those drawings lies the seed of the next generation of explorers. When the object finally recedes into darkness, it will leave behind not just data, but memory. The memory of looking up together, of realizing that the galaxy is not distant but continuous, that our skies are porous. For a fleeting season, humanity remembered its cosmic address. The story of 3I/ATLAS is still unfolding. JWST continues to stream images, a shimmering nucleus wrapped in vapor, a tail that twists like silk under solar wind. Gaia refines its coordinates with each passing hour. Hubble adds ultraviolet snapshots of ionized gases peeling from its surface. Every dataset adds another brushstroke to a portrait of motion that no human artist could ever paint, a living canvas of light and time. What began as a blip in Hawaiian survey data has become a cosmic conversation. Through it, we've learned that interstellar space is not a void but a highway, a tangled network where stars share their fragments like seeds on the wind. Each one carries the chemistry of its birthplace and the scars of its journey. This single visitor has already reshaped planetary defense planning, sparked proposals for ultra-fast intercept probes, and inspired an era of international cooperation that transcends language and flag. Engineers who once designed competing missions now share code and telemetry in real time. For a moment, science itself feels borderless. Yet, the greatest change may be psychological. For centuries, we looked outward, assuming separation, believing the stars were out there, and we were here, watching from a safe distance. Now, an emissary from that elsewhere drifts through our own solar system, responding to our sun, altering its course, proving that galactic boundaries are illusions of scale. It reminds us that our address is not Earth or the solar system. It's the Milky Way itself, a spiral arm shared by billions of wanderers. Soon, as Atlas nears perihelion, its brightness will crest. If the outgassing continues as models predict, it could grow bright enough to be seen even from light-polluted cities. For a few nights in December, anyone who looks up may see a pale green thread stretched across winter skies, an interstellar traveler shining just beyond the moon's path. News stations will broadcast its passage. Families will step onto balconies and point. Some will feel fear, others reverence, most just wonder. In that collective pause, we'll remember what it feels like to share a sky. Astronomers say the moment a light curve peaks is the moment a comet reveals its truth. For humanity, that truth is humility. Our greatest telescope, built to look into the ancient past, has accidentally caught the present tense of the universe, an object changing as we watch, proving that observation and participation are one. Progress isn't about conquering the unknown, it's about bearing witness to it. Exploration isn't a choice we make, it's the instinct that made us. In control rooms and backyards alike, the same emotion rises: gratitude. Gratitude for being alive at a moment when technology and curiosity align to let us see this visitor's glow before it fades. When data from JWST arrives, scientists say they feel a strange quiet. The silence of knowing they are seeing something no human has ever seen before and may never see again. That silence is the closest thing science has to prayer. As 3I/ATLAS glides onward, reshaped by sunlight and gravity, it carries our attention with it. Long after it vanishes beyond Neptune, the questions it posed will linger. How many more wanderers cross these paths unseen? What hidden histories sleep inside their frozen cores? Could one someday arrive carrying molecules that match our own origins? Will we learn to intercept them, to listen, to read their chemical letters? Perhaps that is the true gift of this visitor. Not proof of aliens or omens of doom, but perspective. It reminds 8 billion minds that we too are travelers, a species orbiting a star, moving through space and time with questions for companions. 3I/ATLAS may fade to a memory, but its legacy will endure every time we look at the night sky and remember that the universe is not a place we visit. It is home.